The fundamentals that undergird our existence are nature's tools for implementing relativity. To understand things at or near the fundamental level, you have to understand how these tools work to make atoms and photons respond to changes in velocity. The generally accepted scientific thinking on light does not do well when velocity changes. Their view of light is somewhat rigid, but the speed of light c is relative. It changes with velocity. So that you can understand relative c, I will explain some things about time dilation and how inertia works at the fundamental level. But first, a quick review of the fundamental forms of energy. Space is filled with photon energy from light. We exist in this ocean of energy. All atoms are tiny tornadoes of energy spun from the photons that make up the energy ocean. Our velocity through the energy ocean keeps our atomic tornado spinning like a pinwheel held outside the window of a moving automobile. In discussions about relativity, scientists often assume that two things are true. The first assumption is that all light travels at a constant speed c. And secondly, it is assumed that time slows down as velocity increases. I will use a thought experiment to demonstrate that the speed of light c is relative and changes with the speed of the observer. The actual speed of light must vary so that the relative speed of light will always remain a constant c within the confines of our relative existence. We will consider this thought experiment under three different conditions. In condition 1, we assume a pendulum 1 meter long swings freely back and forth on an Earth-sized planet, and based on well-established equations, it will have a period of 0.61 seconds per cycle. In condition 2, assume that a pendulum 1.26 meters long is used in a similar experiment on a planet that has twice the mass and volume of the Earth. And based on the same equations, it will also have the same period as the previous experiment, 0.61 seconds per cycle. In condition 3, we introduce relativity by accelerating the first planet to 86.6% of the speed of light. At that speed, the mass and volume of the planet would double and its diameter would increase by 26%. It would also increase the length of the pendulum by 26%. And this would establish conditions similar to, but not exactly the same as those described in condition 2. In condition 2, there were twice as many atoms making up the larger planet, but the atoms were the same size as those making up the planet in condition 1. There were the same number of atoms in condition 3 as in condition 1, but the atoms were twice as big. And also the planet in condition 3 was moving at 86.6% of the speed of light. To the accelerated observer, in condition 3, the period of the pendulum would still appear to be 0.61 seconds per cycle, and the pendulum would still appear to be the same length, 1 meter. But an observer relative to condition 1 would observe condition 3 as follows. The planet and everything on it had doubled in mass, and the pendulum increased in length by 26%, but the pendulum was actually swinging slower. It is known that time varies with velocity. It is called time dilation, and the equation on the lower left predicts how time will vary. Lowercase t is any increment in time, a second, a minute, an hour, as measured by a stationary clock. Uppercase T is the passage of the same increment of time, but measured by an observer traveling at velocity v with respect to the same stationary clock. C is the speed of light. Now this is the same equation used to predict change in mass with velocity, implying that time varies directly with mass. Now in each equation, when velocity is 86.6% of c, mass and time both double, as shown on this chart. Now, we apply this experimental result to the notions of light speed. At the initial condition 1, the speed of light is 186,000 miles per second. At condition 3, the speed of light must still appear to the traveling observer to be 186,000 miles per second. But each mile is 26% longer than a mile at condition 1. So 126% times 186,000 miles equals 234,360 miles. And each second has doubled in length. So based on the shorter mile and the shorter second in condition 1, light at condition 3 was traveling 234,360 miles in 2 seconds, which is 117,180 miles per second. Light actually slowed down so that it would seem to our traveling observer to be moving at 186,000 miles per second. Now, if you believe the equations and find no fault in the way I use them, then you can only conclude that the actual speed of light must vary so that the relative speed of light will always appear to remain a constant c. Therefore, the speed of light is relative. All right, let's deal with a new question. Why did the pendulum in condition 3 actually swing more slowly? Of course, we did not actually see the pendulum swing slower. We just calculated that it would based on our equations. But experiments show that atomic clocks run at different speeds when they move at different speeds. So the notion of time dilation has merit. Let's just assume that the pendulum actually swung more slowly, so I can explain how and why it did. To do that, I need to explain the fundamental nature of inertia. The textbook definition of inertia suggests that a body in motion tends to stay in motion. A body at rest tends to stay at rest. But that definition does nothing to explain how and why a body does that. Imagine a spaceship in deep space. An astronaut inside the capsule places a ping pong ball in front of him and lets it go. It hangs there, suspended. Then he flicks it with his finger, sending it racing across the capsule. He repeats the experiment with a golf ball, finger flicked with the same effort, but this time the ball moves more slowly. It is obvious that inertia is related to mass. It is not obvious why either ball resisted the finger flick at all. In deep space, the force of gravity is insignificant and not pulling the ball in any particular direction. Inside the capsule, the air resistance is the same for both balls. Why do the balls resist the finger flick? What force makes the balls want to stay put? The atoms that make up any body work like control surfaces on an airplane. All things are racing through the energy ocean at speed c squared. When the astronaut placed the ball in front of him, the atoms rearranged themselves to fly in that relative position. So when he let it go, it stayed there. When he flicked it with his finger, the force caused some of the atoms to rearrange so that it flew away from him. The heavier ball had more atoms. It would have required a stronger finger flick to rearrange enough atoms to move the heavier ball at the same velocity, so instead it moved in the same direction, but slower. The need to reorient its atoms is what causes a body to resist changes to its existing flight trajectory. Inertia is a body's resistance to altering its atomic arrangement. In reality, a body is never at rest. It is always in flight on a specific course. In the space example above, the courses of the balls were changed by finger flicks. In the pendulum examples, the course of the pendulum was changed by both gravity and velocity. If gravity alone affected the pendulums, then they would have swung at the same rate in all three conditions. But because of a change in velocity, the pendulum at condition 3 actually swung slower. A small airplane, like a Piper Cub, has a top speed of 87 miles per hour. It uses mechanical linkages, cables and levers to adjust its flight controls. Faster airplanes, like jet fighters, can fly at 4,000 miles per hour, give or take. They use hydraulics because greater force is required to change flight trajectories at greater speeds. At condition 3, gravity applied the same force to the pendulum as at condition 2. But the additional velocity through the energy ocean increased the resistance of the atoms to change their orientation in the same way that the increased airflow over the control surfaces of a jet airplane increased resistance to changing its orientation. In the case of the jet airplane, we overcome the added resistance by applying more force to the control surfaces. In the case of condition 3 pendulum, the gravitational force remained the same as in condition 2, but no other force was applied, so the natural response of the pendulum was to take more time to reorient its atoms, and that's why the pendulum at condition 3 swung slower. So you take a pendulum, add a little time dilation, sprinkle in a pinch of inertia, and you get a relative speed of light, c.